Hi everyone, my name is Max Balandat. I support the modeling and optimization efforts on the adaptive experimentation team at Facebook. We have a variety of different areas that we work in, primarily focused on sample efficient optimization. So AutoML is one of them, and so today I'm going to talk about latency-aware neural architecture search with multi-objective Bayesian optimization. This is joint work primarily with David Erickson, Samuel Dalton from my team, and Pierce Chung from Facebook Reality Labs, and there's a lot of other people who contributed to this as well, so thanks to them. The motivation for this is on-device AI. So we have a lot more models deployed to edge devices where there is challenges with regard to memory and processing power. We want to make sure there's a snappy user experience where we have like low latency of the model. And so typically what we'll do is we'll explore the trade-offs between the predictive performance and latency, because there's a natural trade-off between the two. More complex model has higher accuracy, but takes longer for prediction. So this is basically the setting that we're in. We want to explore this. These trade-offs are often non-trivial and reasonably complex and needed to be determined experimentally. And training these models is time-consuming, resource-intensive. So sample efficiency is crucial here. So at the high level, basically what we're doing is neural architecture search. Most of you have probably seen this. We have a loop where we generate new architectures, we're training the model, we measure accuracy, and we actually measure the latency when deploying it on a test bed, an Android device in this case. We get the observations back and basically do optimization of the architecture in order to explore this set of trade-offs. So this is like the high-level setup, and I'm going to tell you how we do this in this particular setting, which has a lot of interesting challenges here. So a little bit of background to get started. Bayesian optimization is a general method for sample efficient optimization of black box functions. Given expensive to evaluate function f, you don't really know a functional form, and you don't have gradient access. You want to optimize that. The strategy of Bayesian optimization is to leverage a probabilistic surrogate model f hat together with an acquisition function alpha. And so the idea is you get observations, you build your surrogate model, you can now optimize your acquisition function cheaply using numerical optimization to generate new candidates. X star, you feed those back to the actual evaluation of f and continue. So that's the basic idea, and it's an established method that many of you probably have seen. The typical surrogate in Bayesian optimization is a Gaussian process, which defines a distribution over functions with the mean function mu and a covariance function k. For instance, the squared exponential one that you see here, where in this case the length scale Li measures the distance for being uncorrelated along the parameter xi. And Gaussian processes are nice because they're non-parametric flexible models that are known for their well-calibrated uncertainty estimates, and we'll use those uncertainty estimates in the optimization. So the other component that we'll need here is multi-objective optimization, right? So we don't want to optimize some kind of scalarized metric. We want to really explore the trade-offs. So we have a vector valued black box function. Typically, there isn't any single best solution that maximizes all of the objectives at the same time. So we want to explore the Pareto Frontier of optimal trade-offs. So in case we're maximizing here, we have a set of possible outcomes. This two-dimensional outcome space here in this example. We get the Pareto Frontier, which is essentially the set of points that can't be improved upon in one metric without hurting the other metric. So there's a discrete approximation of the Pareto Frontier in this case, and that's what we're trying to explore. All right, so jumping into kind of like the actual application that we're looking at here, which is a natural language understanding model. And these are commonly used, by your various conversational agents in mobile devices and smart speakers. The objective here is to understand the user's semantic expression and then convert that into a form that can be used in downstream tasks. The model that we use here, you see kind of like a diagram on the right, is a non-autoaggressive model. And the architecture is depth-wise convolutions with weight sharing. The details here, aren't super crucial. But it's kind of like a standard AutoML task in that we want to identify the parameters of the layers, depths, widths, and so on, in order to optimize the model, and optimize in the sense of trading off the objectives that we have. So we have a search space. After some parameterization, we end up with 24 parameters here, and it's kind of important to do that in a way that's amenable to our Gaussian process models. So a little bit of work that goes into this. The kernel sizes here are represented by integer parameters for the width and length. We currently don't take the hierarchical structure into account. That's an interesting thought, but we don't really haven't really done this here, but we have some ongoing work. This is the search space, and basically, kind of like the problem that we're faced here is quite formidable in the sense that it's a number of features that are challenging. One is that it's a relatively high dimensional search space, 24 dimensions, tuning 24 parameters at the same time. It's not that common. Typically, GPs in Bayesian optimization don't work well beyond 10 to 15 dimensions. We want to do multi-objective optimization. We want to get this done in a reasonable amount of time, so we want to do batch optimization, where we generate multiple candidates that can be evaluated in parallel. And we also have to be able to deal with noisy measurements, and particularly of the on-device latency measurements. All right, so this is kind of like not something you can throw standard methods at. So we use recently developed methods and combine them to make this work. So one aspect here is the modeling. GPs have trouble in high dimensions, typically because distances are very large. These are distance-based kernel functions typically, and because of the cursive dimensionality, you essentially end up with models that end up predicting the mean. So the assumption here is that we're making is that the input parameters exhibit a hierarchy of relevance. So you have some parameters that are really important, some parameters that are of matter importance, and some that are just not important. And so the way we achieve this is by placing a sparsity-inducing prior over the inverse length scales in order to identify crucial parameters, and then use fully Bayesian inference. We use Hamiltonian Monte Carlo to estimate these parameters. So the details here are not all that relevant for the rest of the talk, but I encourage you to take a look at David Erickson, who's on my team, his work on this in UAI from this year. And basically, the upshot is that if you compare the model fit to the right, which is using the sparse axis aligned subspace prior SAAS with fully Bayesian inference, you get a very decent model fit, whereas either a standard maximum likelihood estimate or a fully Bayesian inference, but without the sparsity prior, basically just fail and predict the mean. And so this is in almost 400 dimensions, an example with an SVM model. So this is how we deal with the high-dimensional search space. We also need to deal with the multi-objective aspect. And some background on this. A kind of classic measure of the quality of the Pareto Frontier is the hypervolume, which is the volume that's dominated by the Pareto Frontier and bounded by some reference point R. Larger hypervolume means a better Pareto Frontier. The reference point is typically known by the user optimizer. In this case, it's generally just the setting of the status quo model in production and we're going to improve upon. Hypervolume improvement is the increase in the hypervolume from a new point over a set of points. Say x1 here is a new candidate, and of course, if we want to explore the Pareto Frontier, we want to maximize hypervolume improvement. Now, because GPs are Bayesian models, they don't give only point predictions, but a distribution over outcomes, and so we can talk about expected hypervolume improvement, where we integrate with respect to the distribution of f of x1 here. Basically adding to that, we can also account for noise, which is non-trivial, and there's a recent paper that Sam Dalton, myself, and Eitan Bakshi wrote on this, on noisy expected hypervolume improvement, which turns out to be the one-step Bayes optimal acquisition function for multi-objective BO under noisy observations. Again, details here aren't that crucial, but it is crucial that we use this method to be able to generate large batches of points in a noisy environment for multi-objective optimization. Right, so putting it all together, we have an on-device natural language understanding model. We have parameterized the search space so that it works well with custom process models. We needed to throw sparse axis-aligned subspace priors into the ring and do Bayesian modeling to be able to make the models fit. And we use a novel multi-objective acquisition function that tolerates noise and can scale to large batches. And finally, we basically have a fully asynchronous remote deployment of jobs so that all of this can run autonomously without the human in the loop. And that's basically what this paper is. All right, so talking about what the results that we actually get. So the goal here is to maximize the accuracy of the model and to minimize the P99 latency. So that's the 99th percentile of the latency measurements, and those are measured on device. The metrics in the following are relativized with respect to the production model performance. So like a metric value of 1 is basically the same as the status quo production model. And so we use Q equals 16 batch sizes, fully asynchronous parallelism, and we actually find a architecture that reduced latency by a lot while not hurting accuracy. So talking about the model fits, again, these are Levonard cross-validation plots for our model. On the left two, we talk about accuracy here, and on the right two, we have the latency. And we see that in the map estimate, which is the maximum likelihood estimate, the model is just not very good at all, and essentially just predicts the mean. For the sparse axis-aligned subspace priors, full Bayesian inference, we do get much better model fits. They're not perfect, but they're definitely good enough to do Bayesian optimization on top of them, as we will see. So we apply our method, we throw QNHVI on top of our SASPO model, and we run this, and we get some great results here. So on the left, you see the set of outcomes produced by a quasi-random low discrepancy Sobol search. Essentially think of it as random search. The star here is the reference point. The reference point is the production performance of the model. And we see that, in most cases for random search, we end up with worse solutions, which is not unsuspected because somebody has tuned that model before. There's a couple of points that improve upon. But on the right, we see the results of our Bayesian optimization method. And it's light and day. You see the bottom right here are the better solutions. Right? We want to improve accuracy and we want to reduce latency. So the bottom right is what we want to be at in the plot, and you have a lot more points using Bayesian optimization there. You can see the color coding where in which iteration things were explored, and we see that progressively Bayesian is able to identify the Pareto frontier to the bottom right. There's a little zoom window, might be a little hard to see on this slide, where we zoom into the bottom part because it's a little squished together. And we see that we can get substantial reductions in the latency while even improving the accuracy of the model. And so this was very successful, and we've been applying it to a lot of other use cases since. If we look at the hypervolume metric, also unsurprisingly, we have a huge gain in terms of using Bayesian optimization of a random search here, and we get an order of magnitude larger hypervolume relative to our status quo reference point when we use Bayesian and make continuous progress. So what did we learn? If we compare the new architecture that's found by Bayesian optimization with respect to the baseline, we have it be much wider and much shallower, which isn't too surprising because we know that more layers stacked means more sequential computations and therefore higher latency. But by really increasing the width of the layers, we were able to really recoup that accuracy and be able to significantly reduce latency without sacrificing accuracy. So wrapping up, so this is really kind of a general method for sample efficient optimization of high-dimensional optimization problems, and not just for this particular case, but it worked really well in this setup, and we've been using it for a lot of different applications as well since then. Please read our paper, the ISML workshop on AutoML this year. We've open sourced our methods as part of our open source packages, BoTorch and Axe. You can read more about our work in some recent blog posts, so please check those out. And you can also try it out in an Axe tutorial. Thank you.